So that was kind of the basics of what thermoforming is. Now we'll go through some of the different types of processes that there are in thermoforming. We'll start with straight vacuum forming, and this is by far the simplest technique. In this process, we take the material, the sheet material, and clamp it into a frame, pretty much like we do in the lab here. Heat it until it becomes the sag, like I mentioned in that one slide. It starts out solid, kind of flutters a little bit, then it tightens up and then starts to sag. Transfer the mold to where it seals. On our machine, the sheet comes out, the mold comes from the bottom, goes up into the plastic, it seals, and then you apply the vacuum, sucks the air down through the vents, and then we have a little cooling fan on top that blows air onto it that cools. Straight vacuum forming typically uses a female mold, although we use both female and male molds, just depending on what the product is we're making. Typically what we do, it's easier to make male molds, but you can use either one. So like I mentioned earlier, about the maximum pressure we can have, since we're talking about vacuum, is 14.5 psi, and if you were to go up in the mountains somewhere, you'd even have less. That's quite a bit. Doesn't sound like a lot of pressure, but it's quite a bit to suck that plastic down, that soft plastic down around the parts. Uneven wall thickness is definitely a limitation with straight vacuum forming. You really don't have much in the way of controls to adjust that. We'll see in some of the other processes the main advantage is that we can reduce the amount of wall thickness variation. What happens is the thickest areas of the finished part are where the material touches the mold first. The thinnest areas are where the material is still allowed to stretch, so our corners, and where materials travel long distances are the thinnest areas. The thickest areas would be up near the top of the mold, because what happens is the material touches that, it cools quicker, now it's cold, it's not going to stretch. The hottest parts of the material are going to stretch the most. Now here's a picture of straight vacuum forming. This is our material when it starts, before it gets vacuumed down. As you start bringing the air out through the bottom, through our vent holes here, it starts sucking the plastic down. It goes like that there, and then shows it a little farther down, and then finally down here. And what happens is these areas here, top corners, touch, while the area in the center is still only being touched by air. These areas stop stretching, so it stays the thickest. Now these areas have to compensate for that movement, so they get thinner and thinner until it finally touches the mold and then cools. So our corners, where it moves the farthest, become the thinnest. And you have to be careful, the deeper the draw, we talked about the draw ratio a little earlier, the thinner that material is going to get. You have a limitation on the draw that you can have with straight vacuum forming, because you can't compensate for that thickness variation. Probably one of the most common types, but you do have that thickness variation problem. Very similar process is called pressure forming, and the difference there is that instead of a vacuum pulled on the bottom of the material, pressure is put on the top, so it blows the plastic sheet into the mold versus being sucked from the bottom. The advantages over vacuum forming is that higher pressures can be used. You can use whatever pressure you can get in your plant air. Typically plant air is 90 psi, but you can even get higher pressures if you have special equipment, whereas the vacuum forming only allowed for about 14 psi. Because of that, you can have faster mold cycles and greater dimensional control and part definition, because you have more force pushing it into the mold, and you do it quicker. The quicker you can do it, the less variation you have in the thickness. and in all parts of the part. We look at our pressure forming picture here. Instead of a vacuum being on the bottom, the difference is there's air pressure on the top, so it blows the air on top of the mold and then forces it down into the cavity. There still are vents in the mold because that air that was trapped in this cavity when you first started has to be evacuated, so that air goes out the side, just like you would have in a blow mold or an injection molding mold. The vents are used, in this case, the same as they are in those processes. Those two are the simplest types of forming where you don't have any auxiliary equipment that helps you adjust the thickness of the particular parts. We can move on now to a little bit more complicated processes. This one's called plug assist forming. In this case, the material is forced down. We're still talking about a female mold. The material is forced down into the mold mechanically by a plug. It's not a mold because the plug doesn't have the shape of the part. It just helps force the material down into the cavity somewhat, and then the vacuum is, or it could be vacuum or pressure, is used to force the material the rest of the way against the mold. And the advantages is you get better wall thickness control, especially for parts with deep draws. So it can help force the material down into the corners before it cools so that there's less variation in the wall thickness. We make plugs. They can be made out of many different materials. It could be wood, metal, or thermoset material. At Kerwood, they have a special material that doesn't heat up too quickly. If it gets too hot, for instance, the plastic material could stick around the plug, and if it sticks, it's going to cause some marking. Generally, we could do a plug assist on our equipment. We usually don't because we do such short runs, but we have kind of done it by hand. We do have a top platen that could force it down, but what we would do, say if we were going to make a circle opening, we take by hand, when the sheet comes out, kind of force it down in by hand to get it there, and then it would work. But the idea is that the plug is 10 to 20% smaller than the female mold opening cavity, so it's smaller, forces the material down there, heated near the material temperature. If you get too hot, like I said, you could start getting sticking. Sometimes it's cooled. It works better when it's cooled, just depends on the process. But it forces the material down there before the air is used to actually form it. Here's a picture of it. You can see that this plug doesn't have exactly the same shape as the mold, but kind of similar. So it forces the material down here, so it actually stretches more in this area than it would have with just the air. And then once it gets in this area, it's sucked up against the sides and on the bottom. The idea there is to give better wall thickness control. It's not perfect, and it never is perfect, but it's better than with straight vacuum forming or straight pressure forming. In this case, this is vacuum. I don't know if I have a picture or not, but you could also have pressure air blowing in the top, just like we had vacuum forming and pressure forming. Another process is called reverse draw forming, also called invert forming, pillow forming, billow forming. And this is used when we have extremely or very deep draws. So we have a really bad problem with, by the time you get down to the bottom of the draw, you have real thin material, and it can break too easily. In this case, the material is heated and then blown away from the mold. Also, this is sometimes called bubble forming. The blowing thins the area in the center of the sheet. Just think of it, if it blows up in the center, you're stretching the very center of it. The size of the bubble is controlled by an electric eye, so when it gets to the right amount of stretching, then the air that blows it up is turned off. Then a plug forces the material close to the mold, and a vacuum is used to force the material against the mold. And this allows, like I said, for better control over thickness, but you can see there's a lot more stuff happening than the other ones, so we do have longer cycle times. not hugely longer cycle times, but longer cycle times. We can get fine thickness control by varying all these different variables. Again, it gets a lot more complicated than the other types of forming. We need to determine what temperature do we blow that material at, how warm do we have to get it when we blow it up, what the size of the bubble is, what the size of the plug is, the shape of the plug, how fast the plug forces it down in, when does the vacuum come on, when does the pressure come on, and while it's doing all that, that material is cooling, so we have to be careful that it doesn't cool so much that it becomes too stiff and the air pressure isn't enough to form it. It has many more variables than the other processes we talked about. We have some pictures that shows what that looks like, and these pictures are in your book, and there's descriptions of these processes also in your book if you want to get more detail. You can see we have our sheet here, and the first thing that happens is we blow air pressure from the bottom through the mold, through those vents, forces the plastic up into a bubble, gets to a certain height, and then that stops. And then we have our plug, just like we had in plug assist, force that material that was pre-stretched here in the center down, and it forces the material down into the sides, which it was thicker since this area was thinner, and then gets it in position, and then we pull the vacuum on it and it sucks it down the rest of the way.